Hello dear students, welcome to the subject of structural analysis and design part 3. Okay, I am Professor Priya Kulkarni from Civil Engineering Department of Parvatibai Genba Mose College of Engineering, Wagholi, Pune. Okay, in this session we will look into the design of prestressed concrete. Okay, so before starting the actual design we will see the what are the specifications or what are the standard values and what are the clauses are there in the our IS code, which is IS 1343 2012. Okay, we are going to use this IS code for design of prestressed concrete blocks, end block design, and design of prestressed concrete slab. So in prestressed concrete slab there is one way and two way slab that we are going to design. Okay, so we have seen the design part in our SD2 subject. Okay, there we have seen the design of concrete slabs. Okay, normal concrete slabs by using IS code, that is IS 456. Okay, and here we are going to use the IS 1343 for design of prestressed concrete. Okay, so some part is similar and or some part we are going to use from IS 456. Okay, the basic clauses that are applicable to both normal concrete slabs and prestressed concrete slab. Okay, and this IS code I have uploaded in Google Classroom. Okay, so everyone please go and download it and please see the clauses thoroughly. Okay, and if we are clear with the clauses and if we are clear with the general specifications of design, then we can easily design our prestressed concrete members. Okay, so we will start directly with the limit state. Okay, we are going to use the limit state method of design. Okay, so this is IS code I have opened here in the page number 29, section 4, structural design limit state method. Okay, so or before starting the actual clauses, I'll give some brief introduction about the design of prestressed concrete. Okay, so what is the advantage of designing prestressed concrete? Okay, the prestressed concrete members are ideally suited for floor and roof construction of industrial and educational buildings where live loads are to be supported are of higher order. Okay, so just note down this point. Live loads to be supported are of higher order, and for which reason longer spans between supporting elements are required. Okay, so this is the basic criteria. For that we are going to use the prestressed concrete. Okay, so I'll repeat once again. Design of prestressed concrete or prestressed concrete blocks or members, slabs, we are going to use because if some educational and industrial buildings have live loads of higher order, that means live load which is of large amount. Okay, and for to accommodate that live load, that structure needs to have longer span between supports. Okay, in that case we will use the prestressed concrete members. Okay, so we will provide their prestressed concrete beams and prestressed concrete slab. Okay, so this is the general idea behind the using of prestressed concrete members. Okay, then we'll see one by one the different types of limit state. Okay, that means limit state of collapse, limit state of serviceability, limit state of flexure likewise. Okay, that we have already seen in the design of normal general RCC. Okay, Then limit state, uh, the structural designs shall be based on limit state concepts. Okay, so we are totally using limit state method. We are not going to use the working stress state method in prestressed concrete. Okay, in RCC we have seen the difference between limit state method and limit state of workability method. Okay, so we know the difference. I think you know the difference. If you doesn't know, then please go and check what is the difference and why limit state uh, methods are used. Okay, why those are beneficial and what is the main idea behind using limit state method. Okay, just go and check. Then this method of design structure shall be designed to withstand safely all loads liable to act in this method of design. The structure shall be designed to withstand safely all loads liable to act on the serviceability requirements. Okay, liable to act it throughout the life. It shall also satisfy the serviceability requirements such as limitations on deflection, cracking and maximum compression. The acceptable limit for safety and serviceability requirement before failure occurs is called a limit state. Okay, just see this part. Okay, so why we are going to use the limit state design, or what is the basic idea behind this limit state design is shown or is explained here. Okay, now I'll just zoom in. Okay, I'll repeat once again this statement. The structural design shall be based on limit state concepts. This method of design, the structure shall be designed to withstand safely all loads liable to act it throughout its life. It shall also satisfy the serviceability requirement. It shall also satisfy the serviceability requirements such as limitations on deflection, cracking, maximum compression. Okay, this line. Okay, the acceptable limit for safety and serviceability requirement before failure occur is called limit state. The aim of the design is to achieve acceptable probabilities that the structure will become unfit for the use for which it is intended, that is, it will not reach a limit. Means I will explain this statement in short. What we do in the limit state, we are going to consider all the possibilities, all the possible loads, and we are going to multiply it with a ultimate factor load. Okay, we are going to multiply with a factor of safety. Then we'll before using actual load, we are going to multiply with a partial factor of safety. Okay, so we are going to use, or we are going to provide more load for the calculation of bending moments or calculation of moment resisting capacity. Okay, so actually we are going to use higher amount of loads so that the if some deflection or some cracking, okay, or some collapse, maximum compression, it should not reach that final moment of resistance. Okay, so what we are going to use, we are going to use the more amount of load and we are going to provide safety factors. Okay, so that is the basic idea behind limit state design. Okay, and again in that limit state we have 3-4 parts. Okay, so we are going to check with the limit state of flexure, limit state of collapse, that is shear. Okay, so these are the criteria, and our concrete, that particular prestressed concrete should satisfy all those requirement of higher load or higher movement or higher stress. Okay, so the standard loads or standard stresses should not be sorry, what we are going to use, the design stress should not reach that standard load, okay, that is provided in the IS code. Okay, so we are going to use that is our calculated stress should be lesser than the actual stress or actual stress provided in the IS code. Okay, that is the basic idea behind the limit state. Then before starting with the actual limit state of collapse here, with the actual limit state of collapse, we will first see the limit state of flexure. Okay, the flexural strength, that is bending, that is very important. Flexural strength means we are going to calculate the ultimate moment resisting capacity of that particular beam or slab, and then we'll see the limit state of collapse, that is shear. Okay, this clauses are provided here itself in the IS code. Okay, so we'll see first the flexural strength of prestressed concrete. For that we have to go to the annexure D. Okay, in the annexure D they have provided the flexural strength of prestressed concrete. So we'll see what is that requirement or what is that criteria, and then we'll see the limit state of collapse. Okay, so here is annexure D, it is in the page number 51. Okay, the same if you recall, the same type of criteria annexure D is there in the IS 456 for calculation of moment of resistance. Okay, so same way. Now see here annexure D, which is that included in clause 19.6.2.2 and 23.1.2, same in the IS 1343. We'll see first this part and then we'll go to the respective clauses. Okay, the moment of resistance of rectangular sections on or T sections. Okay, now this is for a beam. Okay, this moment of resistance formula is specially for beams, rectangular section or T section, in which neutral axis lies within the flange, may be obtained as mu is equals to FPB into APS in bracket D minus 0.42 XU. Okay, now we'll see one by one what is the meaning of this statement and what is the abbreviations for this particular short forms. Okay, now what they have said, this case is for neutral axis lies within the flange. Okay, what do you mean by neutral axis lies within the flange? And there is another case when neutral axis lies within the web, or neutral axis lies below the neutral axis. Okay, so these are the different cases, and according to that different stress diagrams are there. Okay, so but in this prestressed concrete design we are going to use this case only, that is neutral axis lies within the flange. For this condition only we are going to design. Okay, why? Now their question arises, why we are going to use only this case? Because we will keep the neutral axis within the flange only. Okay, so we will design or will select such type of sections so that the neutral axis will lie within the flange. Okay, now we'll see the formula. Mu is equals to FPB. Okay, FPB is the tensile stress in tendons at failure. Tensile stress in the tendons at failure into APS, that is area of pre-tensioning tendons in tension zone. Area of pre-tensioning tendons in the tension zone into bracket D. D is the effective depth to the centroid of the steel area. Okay, D is the effective depth to the centroid of the steel area. D minus 0.42 XU. Now what is XU? We know that XU is the depth of neutral axis. Okay, now see here, we are going to calculate movement. How we will calculate the movement? We will calculate the movement is equals to tensile stress into area of the steel tendons into the depth or height. Okay, we know that flexural relation, that is sigma by y, that thing. Okay, that flexural relation. So according to that we'll use this formula, and now they have provided different type So here, for pre-tension members and post-tension members with the effective bond between concrete and tendons, the value of FPB and XU are given in table 11. Okay, these values FPB and value of XU is given in this table 11. Okay, this is table number 11, and here the particular ratios are given, and according to that ratio we'll use the value of FPB and XU. Okay, it shall be ensured that the effective pre-stress FPE after all losses is not less than 0.45 FPU. FPU is the characteristic tensile strength of tendon. Pre-stressing tendons in the compression zone should be ignored in the strength calculations when using this method. This is very important point. It can be asked as a MCQ question. Okay, just I'll repeat this statement and we'll see what is there in the table 11. Okay, this is table 11, right exactly below this clause. Okay, so I'll repeat once again. For pre-tension members and post-tension members with the effective bond between concrete and tendons, the value of FPB and XU are given in table 11. Okay, it shall be ensured that effective pre-stress FPE after all losses is not less than 0.45 FPU, where FPU is the characteristic tensile strength of tendon or ultimate tensile strength of tendon. So just look here what they have stressed over tensile strength. Okay, and the area here in this formula, this APS is the area of what is the FPS? Area of pre-tensioning tendons in tension zone. Okay, so here we are going to use whatever the stress or whatever is the area of pre-stressed steel tendons in the tension zone only. And for that they have suggested one statement: pre-stressing tendons in compression zone should be ignored in the strength calculation when using this method. Okay, so we are going to totally ignore the pre-stressing tendons in compression zone. Okay, so this is very important statement, but this is not the case with IS 456. We are going to add separate sections, that is movement at stress and area. Okay, the force in compression member, and separately we have calculated force in a tension member. Okay, so this is the difference between both the IS codes and both the design members. Okay, in normal RCC and here in this pre-stress. Okay, So in RCC we are going to calculate, or we are going to assume, or we are going to consider the area in tension and compression zone separately, but here we are going to ignore the area or force in the compression member in prestressed concrete. Okay, now we'll see the table 11. It is the conditions at the ultimate limit state for rectangular beams with a pre-tension tendons or with a post-tension tendons having effective bond. So here they have provided two separate columns. Okay, one is for stress in tendons for the proportion of design stress, that is the FPB value, and this is XU value. So whatever FPB and whatever XU value we are going to consider, that is based on the ratio, and will interpolate or will directly take the particular values from this table. Okay, so this table gives this is the ratio. Okay, this ratio will calculate first, and then according to that will calculate the value of PBS, that is tensile stress in tendon at failure, and this is the value of XU, that is neutral axis depth. Okay, so according to that we are going to use this table. Just remember, it is in annexure D, page number 51. Okay, they have one statement: the neutral axis depth in these cases is too low to provide necessary elongation for developing 0.87 FPU stress level. Hence it is essential that strain provided exceeds the required strain by 15% for this case. This is very important statement, or we have to take note of it. Okay, whatever the values that are here in this table for XU, these are very low. Okay, to achieve this 0.87 FPU, to achieve this 0.87 FPU, that is 0.87 FY, what is the maximum, or what is the highest strength that steel tendon or steel tensile steel bars can take? That is 0.87 FY in case of RCC, and here we will use the 0.87 FPU. Okay, so to achieve this value, or to develop this value, these values of XU by D are very low, so we are going to increase this value by 15%. Okay, this is also can be asked as a multiple choice question. Okay, is it clear to you? So this is the flexural strength of prestressed concrete. Okay, now we'll see what is there in the particular clause, that is 19.6.2 and 23.2. so basically I think you have recalled all the things or all the concepts from IS 456. It is in the parallel way we are going to design this pre-stressed member. Okay, I think it is quite similar or quite familiar with you. Okay, now what is the clause? That is a clause number 19.3. so these particular two clauses are there. Those are provided for the design of steel. Okay, design of steel categories. Okay, so we'll see that part while we are going to design. Okay, and in the next session we'll see this limit state of collapse, that is shear. Okay, so I think it is clear to you. Okay, if there are any doubts, please let me know, and mark your attendance by commenting your name and roll number in the comment box. This is very useful, and again I am telling you to mark your attendance in the comment box only. Okay, thank you.